We have arrived at part 8 of the immune system, page 782, where we have a figure 2115 that provides us with an overview of activities here. What happens when we have an antigen-antibody complex? What's going on? How do the antibodies and the antigens interact with one another? And they give us the variety of activities here. Over here we have what could be described as the antigens. Over here we have the antibodies as our symbols. So coming down here right away, we see that we have neutralization. We have an exotoxin, we have viruses. At any rate, there is the prophylactic effect or neutralization effect of completely surrounding an item with antibodies, immunoglobulins. So that's one way of sort of cordoning off something. Then we have something called agglutination. If there is a mismatch of blood type, then the blood that's having the surface receptor, which is A, if you're blood type B or O, and you can't tolerate A, you'll have an immune response to it. If it has the blood surface protein B, and you're a type A or an O, then you'll have a response to that. Similarly, here we have noticed that we have a pentamer here. I'll be getting to that momentarily, but this is an immunoglobulin M, the mu factor. Okay, so then we have, we're going to have a little precipitate here because everybody has bound to a bunch of other everybody's. They've shared connections with each other. We get a precipitation to fall out. Okay, so that removes things from various tissues through precipitation. So there can be some problems with that. One item that it is advantaged by that is opsonization. So we have an immunoglobulin which is bound to a particle here, a foreign antibody, and then because it is having, in the case of an immunoglobulin G, it's having a binding site for phagocytes. So it has an opsonization site, and the phagocyte comes over and engulfs the entire mass right here of the particle plus the antibodies. Over here we have an inflammatory response. These are classic, typical-looking neutrophils. They come along, and they may engage here chemotactically with something. So we have a chemotaxis here. C3b is the chemotactic molecule. It is the opsonization molecule. Another option here is that IgE has seated itself in a mast cell. And then when immunoglobulin E binds to its allergen, could be ragweed or whatever, or danders, then it causes, it sort of wiggles its little butt right there, and it causes the mast cell to degranulate, and we have the release of histamine. So that's an option. Many of us have experienced that if we have some kind of seasonal allergy. Okay, over here we have a slightly different situation in which we get complement activated by the immunoglobulin G. It has a little site there for activation of complement. The complement goes through its cascade, forms a MAC attack. As a result of the MAC attack, we get cell lysis, just the way you like it. Okay, so there's that right there. Here we have class switching, and there's all of these different classes of antibodies, but you need to know the actual sequence. So on the handout, I've given you the sequence. This is the sequence right here on your handout. We have the mu factor, which is actually internal at first. The D factor, the D or the delta, this is the mu M, the mu molecules or proteins. Okay, then we have the D delta version. The D is the first to come to the surface, and it is a surface, exclusively a surface immunoglobulin, and it stays on the surface. And then actually the first to be released is the immunoglobulin M, followed or more or less simultaneously accompanied by the immunoglobulin G. Okay, so mu first, then delta, then gamma. Okay, and usually IgM and IgG are out there together. And then we have immunoglobulin A, so the alpha is the next chain to be made. And then finally the last thing to be made, and it usually requires some sort of chronic allergic response to something or some chronic development of some kind, and that's the epsilon molecule, and it's the one that is activated by type 1 hypersensitivity allergens, danders and pollens and that sort of thing, and seats itself on a basophil or a mast cell and leads to degranulation and anaphylaxis, not necessarily anaphylaxis, but at least histamine release. Okay, so, and then here I've reiterated that. First we have the mu chain, then the delta. Delta can become a surface thing, and then mu is the first to be released, and then gamma is the next thing to be made, then alpha is the next thing, and then epsilon is the last thing to be made. They go over here. Here's the mu thing that's first released, and it's released as a pentamer. Notice that, isn't that pretty? It's very star-like. It's got a little special U-bar right there, a little joiner, as it were. And so it has these sort of like, each of these is sort of like its own little, how shall I say, immunoglobulin G, because it has the factors right there for opsonization and also complement activation. Okay, then moving right along, the next thing that we get here, actually the next thing that we get is the G. And where did they decide to stick that one? That's this one right here. Okay, so this is the immunoglobulin G, and it crosses the placenta, and it's also the gamma globulin in which you have memory. And it's always out there. If you have the immune response to something, you got sick or you got a vaccination, and you're making now lots of immunoglobulin G, that's the one that pathogens run into. Ultimately, after G, we have A. A is found in the respiratory and digestive system. We also have this in mother's milk. It's the immunoglobulin A and the alpha chains here. A little bit different. It's got this little connector right there, just the way you like it. It's a dimer. Okay, whereas the immunoglobulin M is a pentamer. This is a dimer. The surface antigen D delta is right there. That looks not too much differently from the immunoglobulin G. And then finally we have immunoglobulin E, which I've actually drawn a circle here representing a mast cell, and I have immunoglobulin E seated in the mast cell, waiting for its little allergen to come along. When it comes along, we have the release of histamine, just the way you like it. Okay, always remember that we're going to cross the placenta with immunoglobulin G, crossing the placenta. Okay, and then we're going to have A, the dimer, alpha A, immunoglobulin A, in mother's milk. Okay, always remember that for the rest of your life. Those are two easy points on your upcoming board exams. Then we have Class 1 and Class 2 major histocompatibility complex proteins. There are probably the first one that was ever noted was HLA-B27, and HLA-B27 is 95% correlated with ankylosing spondylosis of the back, where the lumbar vertebra tend to actually grow together or ankylose. The bodies actually reach out to each other. They spur at first, and then they cross over the discs, and they actually join up and fuse together. It's a terrible type of thing. It's something that can be avoided, however. It's also associated with colitis and with iritis of the eye. Okay, so at any rate, there are certain major histocompatibility proteins. There is some belief now that the COVID-19, as well as actually lots of flu viruses, tend to attack people with certain markers more than with others. So their genetics plays a role. And who most often comes down with flu, and who in this particular time might actually be susceptible to a COVID-19 infection. So it's not always just age. It's not always just, how shall I say, immune compromise of one kind or another. Although obesity and diabetes, metabolic syndrome, and general stress in general can lead to a reduction, overall reduction of ACE2, remember, which means that the pathogen gets in, but you don't have enough extra ACE2 to break down the inflammatory molecules later on. So that's part of the deal here is we have different genetic makeups that predispose us one way or the other. There's also a predisposition between males and females, and I would submit to you that we have mostly information about males, not that much about females. We'll come right back to this.